Hi, everyone. I'm Natalie Cohn, your community manager for Scale's AI Exchange community. It's a pleasure to have you all tuned in today or this evening, depending on where you are in the world, for our Applied AI series co-production with Tribe AI. Today's event is Applied Natural Language Understanding, Topic Modeling for Text Insights, going from LDA to using advances in language models with Prem Viswanathan. I'll introduce our speaker in a moment, but first I wanted to make an announcement and give you a little bit of support navigating the community platform. After the presentation today, we will host a live Q&A with Prem. If you have completed your member profile, you can join us there and get FaceTime with Prem. In order to make your way to that intimate Q&A, look to the left of your screen for the Agenda tab. Select the Agenda tab, and then you'll see the live Q&A option as a segment within the agenda. Select Join and meet up in a roundtable room where you will mute yourself and drop a line in the chat if you have a question or a comment, and I'll call on folks in the order that I see them in the chat. Alternatively, you can join the live Q&A by selecting the notification Join Now at the top of your screen midway through Prem's presentation. There will also be a networking opportunity after the live Q&A for those of you here today who would like to get matched one-on-one with other attendees and grow your network. In order to join the networking event, similarly drill into the Agenda tab and select Join within the networking segment of the agenda. Please be on the lookout for December's AI Exchange newsletter from me, where I'll announce our December events and links to registration. Today, I published one of our most popular recent events, OpenAI's InstructGPT event with Longwoo Yang and Aaron Kim in article form. I hope you check it out if you're interested in the work of large language models and NLP. Similarly, if you missed the first event of our Metaverse series, Microsoft and Mixed Reality, Revolutionizing Productivity of the Frontline, that recording is now published on demand. On to our guest speaker for the day. Prem Viswanathan is a member of Tribe AI, a collective of 250 plus engineers and data scientists from industry leaders in AI. He's also the co-founder and CTO of SwiftCX.com, an intelligent automation platform for customer teams. SwiftCX.com provides automated monitoring and alerting on various customer experience touchpoints to leadership through natural language powered interfaces. Prem also serves as an adjunct faculty at Carnegie Mellon University, Pittsburgh. Previously, he was the director of ML at Artifact.io, a SaaS startup where he led applied ML research and engineering in NLP. His research is focused on NLP, NLU, and knowledge graphs. Prem has over 10 years of experience in machine learning and building ML-infused products at IBM and AWS. More recently, at AWS, he worked alongside Marinus AI, an AI startup that tackles and disrupts human trafficking, to develop a knowledge graph-powered solution to assist and speed up missing persons investigations by 4 times. Throughout Prem's presentation, please feel free to type your questions in the chat, and he'll answer them intermittently throughout the presentation. Also, don't forget that after the presentation, around 3:40, 3:50, you're welcome to join Prem and I in the live Q&A after the presentation. Now, let's invite Prem to the stage. Hi, Prem. Happy Friday. I think you're still muted.
Yes, my bad. Hi, Natalie.
Hi.
Happy Friday to you as well.
Thank you so much for joining us. I know you're on the East Coast, so this is a little bit late for you. I really appreciate your flexibility there.
Of course, no problem. It's a pleasure to be here.
So just so the audience knows, not only are you the co-founder of SwiftCX.com, as we mentioned, but you're also a member of Tribe AI. And the reason we ended up collaborating here today was because AI Exchange and Tribe AI have been collaborating on this Applied AI series. So it's such an honor to be collaborating with Tribe AI and to have access to such brilliant ML engineers such as yourself. And thank you so much for honoring us today.
Of course, I'm happy to be here.
So without further ado, guys, I will let Prem take the stage. He has a presentation for us, and I'll come back around 3:40, 3:50 when Prem's finished, and I'll further give us instructions on how to get back to the live Q&A afterwards. All right, take it away, Prem. See ya.
Thanks, Natalie. Hi, folks. Again, as Natalie said, good morning, good afternoon, depending upon wherever you're joining from. Thank you for taking the time and joining us here. So my focus on today's presentation is going to be around applied NLU. And within NLU, I chose topic modeling for a specific reason. It's something that I've spent a lot of time on. So the agenda for today is quickly, in addition to what Natalie said, a brief background about me. I've spent about 10 years of ML expertise in large companies and startup. Much of my focus has been around natural language processing and natural graphs. It's more about extracting information from unstructured data and either organizing it as a knowledge graph or serving downstream use cases like topic modeling and customer insights. At SwiftCX, I am a co-founder there, and we build natural language powered interfaces to help with leadership, providing reporting and insights for leadership. So the agenda for today is why I picked topic modeling within natural language understanding. I think it's a great task that encompasses everything you need to achieve within natural language understanding. And then I'll briefly give a survey of traditional methods like LDA and matrix decomposition. We'll go through how to use them and then sort of evaluate the challenges and the evaluation problems you'll face with them. After that, we'll go into the main topic of the day, how to leverage large language models and transformers, the more recent advancements for the same problem, and talk through some of the techniques and challenges that you would come across and how you might be able to leverage them for some of your use cases. So with natural language understanding, essentially it's a subset of NLP with the core objective being understanding the intent or the true meaning of a document or a sentence or a message or whatever that may be. That ability to understand the core intent or the true meaning is essential for question answering, chatbots. It's essential for enabling search. Semantic search is upcoming and very effective today, thanks to advancement in transformers and large language models. And a lot of that ability is thanks to sort of the understanding that large language models can bring to the table. And one other piece within that is topic modeling. Essentially, topic modeling is about being able to understand the intent or the components within a document and organize all of those intents and components into groups or clusters, which then become sort of topic. It's more the ability to sort of understand knowledge from data, and then sort of organize them into groups or clusters. So that's why it's a great task within NLU to sort of where you have to tackle a few things before you build the final model that I hope to walk you through today. And where this is helpful, it's around us on every day, on a daily basis. If you're a user of Twitter, a pretty popular platform these days, you would come across them in trending topics. So recently, I came across this trending topic, and it said 67 in car accident, and it was a little concerning that what happened. I realized there is a car accident, but what is 67 referring to? It's a pretty scary topic to be looking into. But then clicking in very quickly, you realize it's about an individual who was 67 years old, and he passed away in a car accident. Not a great setup, but it's better than the alternative that I sort of imagined in the back of my mind. So topic modeling, as you can see, could help you sort of understand what a large set of tweets are about, but if not done well, the summary or the high level topic representation that you choose can be very misleading and quickly lead you down the wrong path. Now, let's dive into some of the traditional methods that are present within topic modeling. And the most popular one tends to be latent Dirichlet allocation. This assumes that a topic is actually a mixture of keywords, which, like in the Twitter example we saw, totally makes sense. And at the same time, a document from a large corpus is actually generated by a mixture of topics. And this is the critical part. You're not assigning a hard topic or a hard label to a single document. It's almost like a soft label or a soft clustering you would do, where you are allowing multiple topics to be present in a document. This is true for most real world use cases in my experience, and in a lot of data that we come across on a day-to-day basis. Now, not only are these sort of documents generated by a mixture of topics, now each topic, as I said, is a mixture of keywords, and the terms that are part of these keywords have a weightage that is associated with it. And that is where the Dirichlet distribution comes into play. It's a generalized multinomial distribution of the binomial beta distribution. So what it really does is, if you have 4 or 5 categories, it's an elegant way to represent probability distributions between those 4 or 5 categories. And so that's where the Dirichlet comes into play. You use that distribution as the basis, and you assume that all the keywords that are sampled come from that distribution, and hence those keywords form a topic. And similarly, another Dirichlet distribution picks data from multiple topics with a certain probability distribution and then creates the document. So it's like 2 levels of Dirichlet, where keywords form the topic and then multiple topics form a single document. So you start with that assumption, but to sort of identify what the original topic is, you sort of reverse engineer the data point. So I think this picture does a pretty good job of explaining the intuition behind it. If you're looking at a single document, and we start with some random assumption that, hey, this document has 3 topics, the pink, yellow, and blue, to some percentages. And each one of those topics have a certain keywords, and all of those keywords are found in the document. And the main objective of the LDA modeling is then to use something like Gibbs sampling to make assumptions first. Okay, I'm going to randomly assign keywords to topic, and then observe what is found in the data. And then based on the observation, go back and update your priors to sort of come up with the more accurate fit of the distribution. So that's how LDA works, but to sort of enable it and how in practice it really works is, you would start off with some documents like this. Let's say you're trying to analyze review data sets, and if you have 2 reviews, review 1 and review 2, at the very basic form, you would create a document term matrix that looks like this, where you just have a 1 or 0 representation of whether the term is found or not, and you use that data point to then go ahead and make some assumptions that word like movie trailer should be topic 1, slow and Top Gun should be topic 2, some random assumptions. And you go back and look at this observation from the document term matrix, and then you go and update your priors. And binary vectorizer is not the only way to do it. There's many bag of words techniques here, where you can, instead of just using a 1, 0, you could use the count, which is the number of times a term is present in a document, and so on. So a lot of these steps need to be performed to actually leverage LDA and perform the actual topic modeling. Now, the input to the model is these sort of bag of words components. And as you can imagine, the signal that the model can really pick up from is this. So if you go pre-transformers, pre-language models, a lot of us would have spent time feature engineering, and like computer vision, pre-ImageNet, where there was a lot of feature engineering. This is the NLP version of that, where you're sort of feature engineering which words to pick from, and then which phrases to pick from. And the ability to sort of come up with better phrases thereby influences how well you're able to capture the signal from the data to help your model sort of learn. And the success of your LDA oftentimes depends upon how well you have sort of picked up on these signals and the features. And coming up with these features is quite often it derives from linguistics knowledge and expertise, where you're trying to say, yes, I would pick n-grams that are close by. New York is more likely to occur together and not as new and York as two different words. And that you sort of use that linguistic information to update this data. For example, to sort of pick up bigrams, one simple scoring method is you have a score which is generated by counting the co-occurrence of words of WI is new and WJ is, that's just word I and word J, if that's New York. The combined co-occurrence of the word New York would then be divided by the individual number of times new and York is present. And the higher this ratio, the more likely that it is a bigram. And then sort of you use such signals to go and develop your document term matrix. And then from the document term matrix, you sort of use LDA to sort of come up with topics. In fact, this ratio is how early language models, or I would say neural models like word2vec, are able to generate like bigrams and trigrams to then come up with word vectors for those bigrams and trigrams. Now, apart from sort of such statistical methods to pick up those terms and n-grams, a more linguistics informed approach would be sort of you use the universal dependency tree, which is just if you take a sentence, you break the sentence down into its constituent syntactical units, the verb and the noun and the pronoun and things like that. There is the concept of universal dependency tree, which is just maps the relationship between the token based on what sort of tag that they have. And then from this token, you would then say that for my topic modeling, what's really important to me is nouns, because I'm really trying to figure out if it's the chicken or if it's about the dog or if it is about a car or a book. And so nouns is what I really care about. And then you could then use that signal to prepare your document term matrix. And then from your document term matrix, you would then go ahead and use Gibbs sampling, as I explained, to do the LDA. And the output of LDA is, again, keywords. The output that you would get would depend upon the document term matrix keywords that you actually used in the beginning. So as you can imagine, what you get at the output really depends upon what you insert in the beginning in the document term matrix, and hence a significant amount of energy is spent building the document term matrix, selecting the candidates to put it into the model. So your net output and quality of your topic modeling gets influenced by your sort of feature engineering efforts. And this was pre-deep learning days, much of what we did in terms of feature engineering. But beyond the feature engineering side of those things, there is still another challenge when it comes to techniques like LDA, which is evaluation and sort of assigning quality or scores with those techniques. Primarily, it's the main metrics that's typically used in benchmarks and data sets is perplexity. Perplexity is a exponential of entropy. But what entropy really means is if you have a probabilistic function, which is LDA, it is a measure of how many times or how wrong it is when predicting neighbors of a sentence. So you would treat that almost like a language model, and then you would use the probabilistic function to predict terms within that sentence, and depending upon how many mistakes it makes and how correct it is, you can arrive at the log likelihood, and which then informs the entropy. So perplexity is more a metric of how well the probability distribution has learned the underlying data, thereby understood the underlying data. But a significant research out there proving that a high perplexity score does not mean a high correlation to human judgment. And therein lies the challenge. If humans have an understanding of text, and then the metric we are using is not correlated with our understanding and our judgment, then it's unlikely that the LDA models that you use will actually help you align with what a human understanding is of the text. And a slightly better metric is topic coherence, where it relies on degrees of semantic similarity between words. However, when we say semantic similarity within that, it's more about co-occurrence of tokens and not semantic similarity, more like synonyms or what you're more used to in today's world with BERT and so on. So it's still a co-occurrence based information score that still gets used. But the bigger challenge beyond these metrics is that when you use techniques like LDA, your output is still keywords, exactly like the Twitter topic example that I showed you. Those are probably the most prominent keywords that sort of stood out from that corpus of tweets. But it is hard to understand what exactly the topic encompasses. And the list of keywords is not an understanding, is not helpful to convey the meaning of the underlying understanding to humans. So, and as I said, also, it's mostly based on co-occurrence, so semantic similarity like synonyms and antonyms are not really being leveraged. And the other bigger problem with these methods is they use a limited vocabulary. You rely on that sort of document term matrix that I would go back to. And the set of columns is your vocabulary in many cases. And that makes it very difficult to introduce new documents. And if you go back 5 years ago, NFTs were probably never uttered, and you would not have had NFT as a column within that document term matrix. Fast forward to now, it is something you hear about on a daily basis. So now you're suddenly encountered with the challenge of updating your term matrix, and it's not a straightforward way to update those things while preserving the organization of all the historical tweets. What you really want is a topic model or a setup where the historical data is well organized into this nice sort of knowledge graph, knowledge map. And then as we move forward in time, new data sort of either gets bucketed into one of those existing groups, or they're really like created as a new topic because those terms didn't really exist. And doing such things with LDA or a matrix decomposition technique becomes quite challenging. So if we recap the goal of if we say, okay, the goal of natural language understanding is to read a corpus of documents and then organize all the knowledge within that corpus into topics or into sort of some knowledge map. It's just a vague definition. We have the document corpus, we have that. And then we're doing some preparation of the document for LDA, like picking up the terms and so on, which the preparation of document will continue to exist. We still do it today, even with large language models. You could get away without doing preparation of documents. However, in my experience, you're likely to get better results, as I'll explain soon, when you do the preparation. But then the biggest red flags of the prior techniques are a lot of those feature engineering when it comes to tokenization, transformation, trying to use those sort of linguistic signals, and then the actual model itself, like LDA itself, the underlying Dirichlet assumption. I think it's a good assumption, but however, to sort of utilize it, you would need to define the number of topics, and that becomes quite challenging. When you're given a corpus of text, you don't know how many topics there are. So LDA sort of requires you to sort of assume a number of topics and then try to see if there is a goodness of fit. There are like variation of LDA, like Dirichlet process, where it's an unlimited number of topics, but those are quite computationally expensive when you go to a large number of documents. And even with that, you at the end of the day, you get a list of keywords as I described, and that is not a good knowledge map. So those challenges still exist with sort of these old methods. So fast forward to now that we have large language models and transformers, how can we leverage this data points to sort of help us with these 5 steps to solve the red items? So for the first step, let's talk about document preparation. A lot of these large language models are pre-trained on web text. One of the biggest data sources is Common Crawl web text. As part of their pre-training, there is a bit of document preparation. Some portions of the text is omitted, and the model that is pre-trained, like either BERT or GPT-3 or whatever, any of those, they are pre-trained on sort of the cleaner data. So if you'd like to leverage your documents and your data with those models, you're likely to get better results if you sort of try and follow their same pre-training regimen, where you also get rid of these sort of titles of sections or email signatures, for example, to sort of avoid them from being from influencing the model itself. But if you are starting a project as an MVP, I would say just go with the LLM. Don't add any document preparation steps. Start with an out-of-box model where you're using the full document, and then later on go and add syntactic rules to sort of eliminate portions that are either email signatures or headers or unnecessary text from the data. So it's almost like use the full data as is, and then in terms of experiment iteration, remove components out of it. That's usually what gives you the best result. And then moving on to the other challenges we encountered with LDA, where you had to select tokens and try to construct these n-grams and construct these phrases. Thanks to tokenizers like byte pair encoding, we are way better off from where we were. So something like byte pair encoding is a learned tokenizer. And what that really means is with the common crawl data, it's seen every word out there, every sentence out there. And it starts off by assuming every character is an individual, which is an individual byte, as its own token. And then, depending upon how often 2 bytes co-occur, it counts those. And the most commonly occurring 2 words, like a and an as part of an, would then be combined into a single token. And similarly, you keep iterating that loop and combining single individual bytes into group tokens until you've reached a certain number of vocabulary. And that way you have flexibility in terms of how big you want the vocabulary to be. For example, GPT-2, I believe it's about 40,000 is the vocabulary size. So that is learned from the internet text. So even when you go on to encountering new data that is not probably present in the training data, it's relatively does a better job because it breaks down your vocabulary or your tokens into subcomponents, which are like the English language root words. So for example, so this is about tokenizers. Now, apart from tokenizers, the next piece of this component is, as we saw in our LDA setup, where we are trying to merge noun-verb pairs to say, I ate food. That's really using the universal dependency tree to sort of combine something like ate with the chicken as 2 different word pieces and combining them. So how language models, large language models like BERT, leverage this is through sort of combining your the token encoding. So every word in the vocabulary has an embedding. You combine that with the position that the word is present in the sentence, which is the positional encoding. So now you're picking up the pure word level meaning and combining it with where the word is present within the sentence. So you're adding the positional information. And then you're sort of using attention to put those 2 signals together and allow for the attention layer to match up the possible words. So for example, transformers, what they really do is attention layer connects all positions within a constant number of sequentially executed operations, whereas something like a recurrent neural layer would only compare your current token with the previous set of tokens that it has seen. But transformers, thanks to its sort of matrix multiplication style attention, every single token is compared against every other token to sort of pick up on signals. So one example of the signal is like co-reference resolution, which is essentially trying to say let's say a word like it's, if the sentence is the law will never be perfect, but its application. Now the question then becomes, what is it's here referring to? It's here is really referring to the law, because law is the main subject of the sentence. And when exploring the BERT trained model, the pre-trained model, within a certain layer, we are able to see signals of it learning the association between tokens within a sentence and saying that a token like its is essentially mapping law and application. Moving on, so with word embeddings, positional embeddings, and then attention, you sort of solve the tokenization and transformation problem that you would have encountered with LDA. And that only solves the first half of the problem. You still have to learn or pick up on signals and sort of develop the topic that you're interested in. And here, the model, when BERT came out, one of the early large language models, the earlier methods used were, we would use specific positions within the BERT model to extract either a classification signal or a question answering signal or a translation signal. So the way that really operated was, if you would compare that to like parallel ports from back in the day of a computer, each positional pin had a job, and the BERT model exposed so many pins, and you would sort of listen to particular pins to determine what is the result of a classification or what is the result of a translation. Now, this works well for some of those tasks, but if you are trying to do something like topic modeling, which is really a combination of multiple things, you cannot classify if a document belongs to A or B, because a priori, prehand, you don't know what the list of possible topics are. So thanks to a lot of the prompt and newer methods of interacting with these causal language models, where you're not using positional outputs from the language model, but you're rather using the language model's prompt and the output, you're solving the problem of sort of the parallel port, and you're using almost like a modern USB-C serial port to sort of use the protocol to send in the instructions to the model and then get the output from the model. So hence it becomes purely a text in, text out job that sort of gets us closer to where we want to be in terms of topic modeling. And so directly the outputs of these sort of causal language models can then help us somehow build that sort of topic. And let's see how. So this is what I just explained. So back to this problem, we have a document, a corpus of documents. Now give me the topic. Now, when you have multiple documents, it's not really a prompt that you can send out to the model. So you're still stuck with, okay, how do I really solve this? And because when you use a prompt-based approach, the output is still text. It's just not that one large document, it's a condensed text. And GPT-3's accuracy, if you're using something like GPT-3, when even the condensed text is highly dependent on the prompt format. So this paper by Zhao and al. That they presented in ICML 2021 talks about how a simple reordering of prompts leads to a huge drop in accuracy. Now that's one sort of bias that sort of prompt-based approaches have. And the other biases are like majority label bias and common token bias, which is generally applicable to most language models. So if prompt-based approach is better, but to sort of build an automated topic modeling pipeline, we cannot engineer prompts. It's just not a scalable activity. And then if it's so sensitive to prompt engineering, then it's quite hard to build a robust topic model that sort of organizes your data. So then the question then becomes, I'll skip over this. If your output is text and just still condensed, it's just text that is condensed to a smaller space, that's not good enough. But what we really need is sort of some sort of data representation of the document. Now, the default output of BERT or most of these language models are token level embeddings for each sentence. So for example, if I give 3 inputs sentences, and I set the span size to be 128. So the output size from the encoder portion of the BERT would really be, for each one of the sentences, you have 3 as the first axis of your tensor, 128 for 128 tokens. And of course, not all of these sentences have 128, so there'll be the mask tokens towards the end. And then each one of those tokens have 768, which is the length of the BERT dimension, number of tokens. However, what we really want is just one 768 dimensional embedding. And the one easy sort of way to get that is aggregate those tokens. And aggregation here just means like you average it out, the most simplest way. And averaging out works pretty well, actually. So to recap, you have a single sentence that goes through the encoder portion, and every token in the input sentence has a positional embedding that gets resulted. Now you actually average out those token level embeddings to form the entire sentence level embedding, or rather the document level embedding. So that way you're sort of able to get a document representation. So you're moving away from text in, text out to a text in and an embedding out model. And once you have an embedding out model, you could then go ahead and run clustering on it to create the clusters, and those clusters will become the topics. Now, I want to focus this talk more on the LLM side of things. So in terms of clustering, UMAP and TSNE are like commonly explored approaches out there, but they're not very good for like sort of an automated pipeline and also to build deterministic sort of clusters. So hierarchical clustering is a better approach. You do not have to mention the number of topics, so that's attractive. And then it's not very scalable. So using an approach like Grinch, which came out of the UMass, University of Massachusetts School, is slightly more scalable than straight out of the box hierarchical clustering. And a few generalizations or a few improvements on hierarchical clustering is something like scalable agglomerated clustering. And instead of merging 2 items on an individual basis, this would go on to sort of make multiple merges at each step. So let's assume clustering is perfect and we have sort of solved that problem. So to achieve good topic modeling and those final results, what's the best lever that we can sort of control? Often turns out to be the actual language model, large language model, and sort of how you use the input data to sort of generate the embedding. So that is the high leverage item in this pipeline that you can sort of control the most. Clustering is most often a deterministic model, and you want it to be deterministic. So what you can really control and fine tune and train is your language model and then the embedding portion of the setup. So when you want to control the language model, often the challenges are like a document level representation is quite often aggregation of too many things. I'll show you an example. So then the option becomes, what else can I do? You could probably break the document into sentence level or a sub-document level and then get representations for those sentences or sub-document portions. So for example, if you took a Amazon review like this, and a middle of the road review that says, actually has many signals within it. He's talking about active noise cancellation. This is a review of a Bose headphone. He's talking about, I will act that this device not having active noise cancellation. He talks about how this sound or volume level of this is not great. And he also talks about how the 3.5 mm cord doesn't exist within the package. So multiple knowledge or signals are present in this sort of one document. So if you're trying to get a representation for the entire document, you're never going to be able to get those accurate details within it. So for example, if you just did a semantic similarity between that review and something like, I love how the materials feel and I love how the fit feels, if these were the 3 reviews that you're sort of trying to organize, there's very high correlation or similarity between 2 and 3, whereas 2 is talking about materials and 3 is talking about the fit. They shouldn't really be. Whereas something similarity between 1 and 3 is quite low. So to sort of improve on these, I'll skip on these few slides in interest of time. So the next option becomes, okay, instead of generating the entire document level representation, I'll break it down into sentences and use the sentence. Turns out that's good, but not good enough, because a single sentence can still have a lot of fluff and miscellaneous information that's not really centered around our core insight. So then the question is, how do we tackle this challenge? So when you develop a embedding from a sentence, you wouldn't be able to sort of extract every signal from the sentence. So what you really want is grounding of the core subject within a sentence. So by averaging, if you go back to mean pooling, what we are really doing is averaging all the tokens. And therein lies the problem. You want some tokens to be given more importance and some tokens to not be given more importance. But so how do we do that? One way we could do is leverage sort of linguistic features like frame of a sentence. The frame of a sentence is essentially a verb predicate pair. So the assumption is every English language sentence focuses on who did what to whom. And so in this case, this frame focuses on the verb feel, and the arguments for those feel are, I feel they are loud enough. So what we do to develop a better representation is to give a higher weightage to the arguments of a frame when you're doing the average pooling, and lower weightage for the remaining tokens. When you do that, turns out the similarity of sentence 1 and 3, which is basically sentence 1 is the one long sentence, but now instead of doing an average pooling, we're giving more weightage to a few tokens, and you're using sort of that signal to compare with the third sentence, which is talking about the lighter feel. So in this case, it's 0.41, so it's much lower, which is good. But then the first sentence, which is about volume, in comparison to fourth sentence, is about 0.77, which is a much better improvement over what we saw in the past, which was 0.48. So this is semantic similarity. So in this way, picking up on signals from within your tokens and weighting some tokens more than the other when you do average pooling to arrive at the document representation, you're more likely to get a better result than when you treat all those tokens equally. So now you're starting to see combining sort of those linguistic features like frame with the large language model features like embedding, and giving different weightage to sort of these methods. But in practice, this does not really work very well from what I've seen. The primary reason is for a single document, you would get n sentences. And then from each sentence, you would then get m frames based on each verb and predicate pair that it has. So quickly, a document exponentially increases in terms of candidates for topic modeling. And once you expand that so high, it quickly becomes unmanageable. And then the clustering task becomes quite difficult. And you have a lot of noise also that increases. So one document would have 2 or 3 signals, but when you use these frame, while extracting those 2 or 3 signals out, you would have added 10 or 20 irrelevant data points from the sentence. So that's the challenge with sentence level. So if sentence level extraction representation is challenging, then what do we do? Then that's where the sort of leveraging large language models to sort of prompt-based extraction of subsections within documents is very helpful. Essentially, one way to do this is you have the document, and then you would ask very specific questions about what are the key features you talked about. And the large language model, if fine-tuned, will do a good job of giving you the key features. And then you go back and ask questions about those key features. So for example, here I'm asking the first question, what are the key features the reviewer talked about? The answers are noise cancellation, fit, and volume. And then you ask a follow-up question to saying, so what did he say about the fit? Now the answer is more concise and to the point where it says, I like how they fit. So using such setups, now the entire document is broken down into 2 or 3 components that have the key signal. I like the fit, noise cancellation doesn't exist. And this is great because we have reduced the large document into key signals that we want for our model. Turns out large language models, when you sort of question it this way, they speak up and they give you the signal, which is perfect for us for the topic modeling task. When you start grouping these signals together to form clusters, then you have a better understanding of rather trying to group the whole document as a whole, the one document as a whole. Now, one challenge you would often encounter with this is if you take this approach, sometimes when they give you an answer, they would also sort of make up stuff. This happens more often than you think. And what can we do to sort of guard ourselves against it? One out-of-the-box technique is basically use the answer and ask like a yes or no question. Now, quickly, you can imagine you started with the first question, which is what are the key concepts? And then you ask explanation for each key concepts. And now you're trying to ask another question per explanation, trying to say, is this explanation true or false? So the amount of prompt interrogation quickly expands and it becomes expensive. And you'd have to also train the model to sort of do these things. A slightly easier hack or out-of-the-box solution is to sort of compare the answers to your key concept question to sort of every sentence in the document, and thereby use sort of semantic similarity, a basic cosine similarity score to say, okay, did the answer GPT-3 gave me, was it actually present in the document? And if it was present, then it's more likely to be truthful. And if it wasn't present, then it's likely the GPT-3 is making up stuff, or any large language model for that matter is making up stuff. So it helps you sort of verify the answer that is given. Now, the added incentive of this is quite often when you build these pipelines, when you're showing the topic and you're trying to show where did this topic come from, using the same language the user used helps with attribution and referencing the original document. And that results in sort of a transparency to go from, okay, this is the topic summary, and this is the topic members, and this is the sentence from within the document where I actually extracted this topic. And so we've explored the sentence level setup and then the document subsection level setup. And there are many ways you can sort of interrogate. One example, like how I said, was you can ask like, hey, what are the key concepts? But then the other examples people have tried and it's pretty effective is asking about, okay, what are the topic themes? Maybe it could be what are the main complaints the users have? What are the main positive feedback the users have, and so on. Now, of course, all of this is domain dependent. If you're in the biomedical domain trying to do this, you'd probably want to be asking different questions that are informed by the domain. Now, the remaining last piece to this puzzle is, great, now that I'm able to extract signals from these documents, and I have ways to sort of pick up on these signals through interrogation, question, back and forth. Now, what actual language model do I choose? This is where, in my opinion, generally the research and trend out there is the more parameters, the better. So you use a larger model with much more parameters, your question answering is going to be better. And if your question answer is going to be better, then your downstream topic modeling will be better. However, from what I've seen, you're more likely to get better results by fine-tuning middle of the road, sort of the T5 model. Flan T5 is new, and if you have heard good things about it, it's not something I've tried, but T5, the 11 billion parameter model, is pretty good. And what you would really do with this is fine-tune that model for both the question answering, sort of the interrogation, and then one of the most important things you want to do at that point is for every question answering task, also automate in your training pipeline to sort of formulate that question answering also as a truthful verification question answer. So that way, that becomes part of your training regimen. And then having multiple formulations of the same objective will give better results. And also the other big thing you want to be doing is using the same model on multiple tasks. So if you're going with keyword extraction to sort of pick up on those key signals, fit, the volume levels. And then if you're going for the question answering approach, and then using the same model to generate the embeddings that then get clustered, you're more likely to get better results when you're using the same core large language model for all 3 tasks. So train one model on 3 tasks is better for robustness. And anything you do in this experimentation will have to be underpinned by evaluation metrics. And one common evaluation metric people do is sort of the semantic similarity level. You get the embeddings and you try to say, okay, are the embeddings similar, yes or no? But from my experience, you get better results when you go all the way to the end and then try to compare the resulting clusters with human curated clusters, and then see how the entire topic modeling pipeline worked. So in terms of semantic similarity, I didn't want to talk much about it, but I think all the work by Niels Reimers, who's the creator of SentenceBird, he has covered everything pretty exhaustively. I would refer you to that. That is the last component of my presentation. Okay. Open to questions.
Thank you so much for that, Prem. It's obvious that you're a teacher. That was a great instruction. So we only have a few moments, but maybe we can let the audience ask some questions face to face. So we'll transition away from this live stream into the community platform. If everybody looks to the left-hand side of their screen, there's an agenda tab. You drill into the agenda tab and you can meet us in the roundtable. Actually, we have one question in the chat right now. Don Liu, instructor at Denver Chinese School, says, "Hi, Prem. I'm wondering if you have any recommended learning resources, i.e. textbooks, online courses, topic modeling. Thanks, Don."
Yeah, that's a good question, because I don't have an answer to that. So in terms of resources, I may be a bit biased, but for LDA and the sort of traditional probabilistic topic modeling, the lectures and coursework by Eric Zing, who's a professor here at Carnegie Mellon, he does a great job. I would also look into research that is coming out of UMass, University of Massachusetts. They do a lot of linguistic research, and of course, Chris Manning, his book and his courses do a great job. And there's one other professor that I'm forgetting, but I'll look it up and then type it here in the chat, which is a pretty good book in terms of linguistics and then going into sort of feature engineering side of the world. Now, in terms of the BERT and sort of that world of topic modeling, I would refer to I think it is SentenceBird for the semantic similarity, but also TopicBird by Martin Grondhost. I'm probably butchering his name, but I would search TopicBird, and he's the creator of the package, and he does a pretty good job of exhaustively looking at all the combinations of embedding and clustering, which are really the big 2 pieces. But what I wanted to focus on was what is the input to your embedding, and how you can sort of control that to sort of make your life easier in the world of when you get to clustering. Yeah, hope that helps.
Awesome. Okay, so there's probably a notification at the top of your screen right now. You can join us in the roundtable live Q&A that way, or you can go to the agenda and then the live Q&A join now. I'll meet you guys there in less than 30 seconds. And if you have any additional questions for Prem, meet us there and ask him face to face. See you guys soon.